All right, hi everybody, welcome back to chapter 2's lecture videos. In this one, we're going to cover a couple of different concepts around velocity. We're going to talk about how we're going to treat time, and we're also going to distinguish velocity from speed. We are going to also talk about velocity versus time graphs for the first time, and we'll also discuss how those graphs are going to come into play later on. For now, let's just introduce some of the basic concepts. First is going to be time. When it comes to time, time is going to be defined as a change, never as an instant. In other words, what we need to know is how much time has passed from the beginning of a motion to where we're trying to analyze. We do not necessarily need to know exactly the time, like on a clock. We need to know amount of time passed. Our SI unit's going to be seconds. So anytime you're given, if it's in hours or in minutes, you need to convert it to seconds. The number one thing that we have to do in this particular class is we have to convert everything every time. So if we're given something in kilometers, we want to convert it to meters because that's our SI unit for distance. If we're given a time in minutes, we want to convert it to seconds because again, that's our SI unit. And all time, velocity, and speed are going to have standard units, not just this one. All right, so then if we talk about delta t, remember that delta means change, then what we're doing is we're taking the final time from whatever motion we're looking at minus the initial time. Now, every time that we start or every time that we're analyzing, we are looking at an initial and a final. The initial, however, can always be defined as 0. And so instead of writing delta t equals tf minus t0, remember f means final, 0 means not or at the beginning. Since t0 will always be 0, delta t just becomes t. And you'll see that that gets simplified in most of our equations as just t instead of writing delta t. Just so you're aware of why you're not seeing the delta anymore in our equations, because we're assuming that at the beginning of a motion that we can set the elapsed time to 0. Okay? All right, next is going to be velocity. And so we're actually going to take the average velocity equation, which says change in position, that's delta x, x final minus x initial, divided by change in time, again, t final minus t initial. But remember, we also just said t0 is going to be 0, so we already know one of the variables in this 4-variable equation, and that's t naught. So instead of writing tf minus t naught, we're just going to write t on the bottom of that reaction, or on the bottom of that equation, sorry, still in chemistry mode. All right, so that means that average velocity, that's what that little line means, average velocity can be total distance divided by time, or total position change divided by time. With velocity, we don't want to just say distance, we want to say total displacement. And the reason is velocity is a vector, just like displacement is, and it needs both direction and magnitude. Our SI unit for velocity should be meters per second. So in other words, if we are not in meters per second, as far as position or time is concerned, we have to convert it. The average velocity of an object isn't really going to tell us anything about the overall trip. It's just going to tell us how long did it take. So in order to analyze motion a little bit closer, we're going to look at velocity time graphs, and we're going to see how the overall motion of an object may be different than the average that we're simplifying it to. And so we take our velocity information and we're going to think more about instantaneous velocities. So this is if I could point a radar gun like our police have to catch people who are speeding, if I could point a radar gun at a car or an object that is moving, and it would tell me both the direction and magnitude of the velocity, then I know that I've looked at an instantaneous velocity. Now, the difference between this and a speedometer is that a speedometer, an actual radar gun, cannot tell you direction. It can tell you how fast something is moving, but it cannot tell you which direction it is going. So mathematically, when we're looking for velocity, we're just looking at taking a limit. This is a calculus operation. You don't have to worry too much about this. When we look at instantaneous velocity, a lot of times what we're looking at is a graph to interpret where a velocity is on a graph at a specific instant in time. So again, the calculus part of this is helpful to know. That's why I wanted you enrolled in calculus while you take this class, but it is not necessary to know. And at some point over the course of this year, you will find that some of the stuff you're learning in that class overlaps with some of the stuff that we learn in this class. I will teach this class as if you are not in calculus, but it does help to understand like what a limit is and what a derivation is and how, finding the area under a graph is really, really useful, especially when we get into our velocity time graphs. Next is going to be our speed. So speed is going to be, like we said, a scalar with no direction. So if I point my radar gun at an object, it'll tell me how fast the thing is moving, but it will not give me any information about direction. And we can get an average speed similar to the way we got average velocity, other than the difference is that with velocity, we put displacement on top of the equation. So that means that the movement from the 0 point changed at some point and stopped at some point from where it started. Whereas with an average speed, we're just looking at total distance divided by total amount of time. Speeds do not need direction. They just need a value. All right, so here we have our example of a trip to the store. From home to the store and back is a total 6-kilometer round trip. Now, if the average speed was 12 kilometers per hour, the displacement is going to be 0. So think about the average speed in 12 kilometers per hour, meaning 6 kilometers over 30 minutes. That's our speed, aka the total distance that we traveled there and back, divided by the total time, 30 minutes. 6 over 30 is going to end up being 12. If we convert it to our hours, which is the unit that they have reported this in, I would prefer you do everything in seconds and meters. So I would ask you to convert your minutes to seconds and your kilometers to meters. But I digress. The displacement for the total trip, since we started at home and ended at home, is 0. And that means the average velocity must have then been 0, because displacement is what goes on top of our velocity equation. All right, so here we have a couple of our first introductions to graphs. On the far left, we have position versus time, is exactly what you think. We're tracking where we start in a motion, where we go, where we end up, how much time it takes. And this is our trip to the store. So we went from the home point, which is 0, to the store, 3 kilometers away, and then we came back home, and it took us this amount of time for each one of those different motions. Now, if we look at our velocity time graph over that motion, from the initial trip to the store, our velocity was positive because we were moving away from the source or the home point. And then our velocity is negative when we move back towards the house. At one point in time, it is, of course, non-defined, also known as, like, we don't care. And so your velocity time graph comes out to look a little bit weird, like this one over here. Now, and this, of course, velocity time graph takes into account direction, which is why you see the negative velocities and positive velocities. As you move away from your source, your velocity is positive, and then if you move back towards it, that would be negative. Over here on the right, we see a speed versus time graph, where we just kind of track how fast the object is moving the entire length of time that it is moving. And we don't care what direction it's moving. So this is a flat line, all at 12 kilometers per hour. Now, we are going to practice with these velocity time graphs. Do not worry too much about these right now. Right now, what I need you to understand is position and velocity. Here we have a practice problem. I'd like you to just kind of walk it through with me. We've got land west of the San Andreas Fault in Southern California is moving at an average velocity of about 6 centimeters per year northwest relative to land east of the fault, aka we could break off a chunk of it. Los Angeles is west of the fault and may thus someday be at the same latitude as San Francisco, which is east of the fault. How far in the future will this occur if the displacement to be made is 590 kilometers northwest, assuming the motion remains constant? All right, so how are we going to set this up? I think I'm going to do I'm going to do these in class with you when I'm back on Tuesday. There isn't a quiz or anything coming up anytime soon, but I do want you to work on those problems that I posted over 2.1 and 2.2 that had a few velocity problems. I'm going to table this for now because I want to go over these with you in person, just to make sure you're understanding where we're getting our numbers from. So I'm going to skip ahead a little bit to 2.4. where we're going to just introduce the concept of acceleration. So we took our velocity. Remember that our velocity was defined as change in displacement over time. Okay. Our displacement over time over here. And then our acceleration takes it a step further and says, well, change in velocity over time is going to be the next thing that we analyze. And acceleration is going to be one of our two derivatives. So in calculus, you're going to learn about the first derivative, the second derivative, and the third derivative. And I believe you also discussed the fourth, but I don't remember. Acceleration is our second derivative. The first derivative was velocity. The second is going to be acceleration. And basically what we're doing is we're taking the previous motion. So velocity took, like if we put this as position, velocity basically takes the previous motion and analyzes the change in and calls itself velocity. We analyze the change in velocity and we call it acceleration. And that's the best kind of like introduction to those that I can call or that I can talk about for now. But honestly, just understand that what we're doing when we say position, velocity, acceleration is we are analyzing the change in the previous one to determine the next one, right? So we have to look at position in order to get velocity. We have to look at velocity in order to get acceleration, and so on and so forth. That being said, our overall equation is going to be A is going to be change in velocity over time. We're going to look at our SI units, again, meters per second squared. We're going to stay in the similar units as before. Time should always be in seconds at this point. Velocity is going to be a vector, which means that acceleration is a vector. When we say it's a vector, we mean it has to have both magnitude and direction, no matter what. And remember that direction can be as simple as positive and negative. And we'll talk a lot about how acceleration changes the speed of an object or the velocity of an object here in a little bit as well. We're going to practice this a lot. And a lot of times when we talk about objects accelerating, we use them in the wrong way. So we say the words wrong. And one of the things I'm going to point out is that when acceleration and velocity are both moving in the same direction, aka an object is accelerating in the same direction it is already moving, the object is going to speed up. And this is how we have always classically defined something as accelerating. I think the most common version of the term acceleration that's used in our day-to-day lingo is going to be of a car. So we say that as a car gets on the highway, it accelerates in order to match the speed of other cars on the highway. When we say that acceleration is in the opposite direction of motion, we say the object is slowing down. This is absolutely true, but a lot of times people use this word deceleration. Okay? The term deceleration is incorrect. What we actually should be saying is we are accelerating in the negative direction. And the reason is, by saying we accelerate in the negative direction, we're still implying a change in motion is occurring, and we're giving ourselves information about what the object is doing. Deceleration is more of like a, I want to say like a slang, and you'll hear books and texts use it. It's not the first time, it won't be the last time, but just understand that in physics, a lot of people are very particular about you saying acceleration in the negative direction over deceleration, mostly because accelerating in the negative direction gives us more information about the motion that is originally taking place as well. All right, so here we have an example of acceleration. Up here I've got car A, and that's this one. Oh, I'm sorry. Actually, I think we're supposed to identify which one's which. Up here, I've got a few different cars on the right, and then I've got the arrows that correspond. And what we want to do is we want to identify which of these cars represents these motions. Remember that arrows represent vectors, meaning both direction and magnitude. So for instance, in A, we see the arrows getting longer, and they're all pointing to the same direction. So if an arrow represents a velocity at any point in time, this arrow's velocity is getting larger and moving in the same direction, which means that the acceleration is positive and the velocity is positive. Since we're pointing to the right, we're going to say, excuse me, that to the right is positive, and as far as velocity is concerned. So arrows to the right for V positive, arrows to the left for V negative, and then acceleration is determined based on that. If the arrows are getting smaller and pointing the same direction, then we know that the acceleration must be negative. If arrows are getting larger and pointing the same direction, then we know that the A is positive. And this is only for positive velocities. For negative velocities, if the arrows are getting longer and pointing in the same direction, acceleration is positive. And if the arrows are getting smaller and pointing in the same direction, the acceleration is negative. This is kind of how to interpret the different arrows. So let's do this first one. A, we have we have arrows getting longer and longer and longer, all pointing to the right. So the velocity of the object is positive and the acceleration of the object is positive. And that looks like this first car right here. Hopefully you see why. What this means is that our car is accelerating to the right and it is speeding up. So I can ask you questions like, is it speeding up? Is it slowing down? All right, let's look at this next one. We've got arrows pointing to the left and they are getting longer. So velocity in this case, since it's pointing to the left, is negative, and acceleration must be positive because the arrows are getting longer. And that is, according to my letters on the left, that's letter D. All right, next one is going to be this guy. Velocity still negative because it's going left, and then acceleration, because the arrows are getting smaller, acceleration is going to be negative. So looking up here, I've got letter E. Down here on the right, again, we have velocity positive because the arrows are pointing to the right, and we have the arrows getting smaller, which means that acceleration is negative. The object is slowing down. So this is going to be, I think this is letter B. And then over here, so this object is slowing down, sorry. So we're going to write that too. It does say to describe motion on the problem on the left. Over here, this object is also slowing down because acceleration is in the negative direction. Over here, this thing is speeding up. This one is also speeding up. Remember, anytime acceleration is positive, the object speeds up. Anytime acceleration is negative, the object is slowing down. All right, then down here, we have arrows that are all the same length, pointing to the right, so we know velocity is positive. But what do we know about acceleration? Well, the objects aren't changing size, so since there is no change in velocity, delta V over t is 0, which means A is 0. So this object is moving constant and 0 acceleration, okay? And again, something we will practice much with in the future, okay? All right, here we have some velocity time, position time. We have position time graphs. I'm gonna, again, table this for our discussion on Tuesday. We need to talk about graphs in person so that you get the hang of it. I can talk about it here. For instance, we see position time in this graph. Our position starts at 0 and gets to be more and more positive as we go up. This is exponential motion. We're going to talk about how to translate the position time graphs into velocity versus time graphs, and then from velocity versus time graphs into A versus time graphs, acceleration versus time graphs. I'm not going to do that here, mostly because it involves teaching you how to take a derivative. That being said, derivative is just like please don't freak out when I say words like that. I'm going to teach you how to do this visually. You don't have to do any math in order to interpret these graphs. All right. I believe that that is all for our acceleration. We've got instantaneous versus average acceleration. Average acceleration is going to be a conversation we have here in the near future. Basically, whenever we talk about motion, all motion, if it's undergoing acceleration, we will assume has constant acceleration to make our problems possible to solve. In this class, we are not going to be looking at overall motion. See, here we have a motion that has different accelerations at different times. We are not going to be able to analyze motion in a mathematical sense using something like this, but we can look at a graph and say, for the first second of this motion, the acceleration was positive, meaning it sped up. For the next 2 seconds, from time 1 to time 3, the object was slowing down because the acceleration is negative. Then we can say our acceleration was 0 for a second and a half or so, and then we can say it was positive. Then we can say it got even more positive, and then we can say it got very negative at the very end, right? So all we can do with graphs like this is look at like an idea of motion. This looks like something was speeding up, then it had to slam on its brakes, then it kind of went constant for a little while, then it started speeding up a lot, then it had to slam on its brakes again in order to come to a complete stop. And if we ended up with acceleration at 0 at the final time, then we would know the object had stopped changing motion and was moving in a constant way. That being said, Instantaneous acceleration is useful in a graph sense, but not necessarily in a mathematical sense. These are all problems that we are going to go through. This is an example of position time, velocity time, acceleration time graphs. Again, I'm going to go over this with you in person because I feel like talking about this on here is not adequate. And I want to be able to kind of go through some different types of position time graphs and how I analyze them. I think it makes it a lot easier than what you see in your book. Okay? All right. Well, I'm going to stop us there. And I will hopefully see you on Tuesday. Have a great weekend.